Okay, we're going to continue on talking about the reactions of aldehydes and ketones, and we're going to start with the formation of cyanohydrids, and then we will go back to looking at the acetals and ketals. But this reaction is fairly straightforward. What we're going to do is we take an aldehyde or a ketone and react it with HCN. Now, this is normally done in two steps. The first step is to react CN minus and then add H plus, because HCN is a little bit of a toxic gas, and so we don't want to mix those together. So if we're reacting our aldehyde or our ketone with a C triple bond N molecule, which this is cyanide, right? So hydrogen cyanide is probably not exactly the best gas to use. But if we use cyanide ion, that will attack the carbonyl, and the pair of electrons will go up to the oxygen, just like a normal Grignard reaction. And so I'm going to end up with an O minus with then the C triple bond N group down here. And then in the second step, I'm going to add H plus in order to react, well, in order to protonate the OH group and form the in order to form the OH group. So that will give us a C triple bond N added to the carbon, and the carbonyl will become an OH. Now, whether this is an aldehyde or a ketone, this is what is called a cyanohydrin. And in your textbook, and in most textbooks, they're always talking about cyanohydrins. There's always a picture of a bug that is spraying one of its predators so it doesn't eat it. What happens is that that bug has a cyanohydrin in its system, and what it can do is it can actually reverse this process and basically spray the predator with hydrogen cyanide, which probably won't kill it, but it'll keep it from being eaten. Another aspect, though, of cyanohydrins that we can use is once you form a cyanohydrin, then we can talk a little bit about what a nitrile group is, and we did that a couple days ago. But let's go ahead, and so if I have this cyanohydrin molecule, a nitrile, which is a C triple bond N group. A nitrile is a carboxylic acid derivative. And I listed those the other day. Carboxylic acid derivatives are called carboxylic acid derivatives because when you react them with H plus or H2O, you will end up forming a carboxylic acid. So the C triple bond N group here, if I was to treat this with H plus H2O, I would do what is called, and this reaction is called hydrolysis. So we hydrolyze the nitrile group or the cyano group, either one. And what we would end up doing is we would end up converting that nitrile group into a carboxylic acid. We'll talk about the mechanism of this when we get to carboxylic acid derivatives in chapter 24. Now, if I rewrite this structure, I can rewrite this sort of in a line. We're also going to find when we start doing more carbonyl chemistry is that the numbering scheme for a carbonyl compound is actually using Greek letters, and it starts with the group next to the carbonyl, and so this is called an alpha hydroxy carboxylic acid would be sort of a generic name for this. So in making the cyanohydrin and then hydrolyzing it, we actually have a pretty good way of making an alpha hydroxy carboxylic acid. Now, these are used quite often in moisturizers. They have a very good property of being able to absorb water and hold water in. So they're used a lot in those types of molecules. And I'm just looking to see if the hand cream I have here on the desk has it, and it does not. So sometimes you'll hear about these alpha hydroxy acids. I think there's probably some commercials on TV where people put those on their face to remove wrinkles. So other than the bug using the cyanohydrin to convert it to HCN and spray its predator and keep from being eaten, this is another synthetic way that cyanohydrins are important, is in the preparation of alpha hydroxy acids. Now, let's go back and talk a little bit about acetals and ketals from the last lecture. So what we did last time was we took an aldehyde or a ketone and we added two equivalents of something like methanol to it. We said we had an equilibrium reaction with acid as our catalyst, and we end up forming first, from the first equivalent, we end up forming, and in this case, this came from an aldehyde. So this is a Hemiacetal. And then if we add the second equivalent of methanol to this, we're going to end up forming, having two OCH3 groups attached to our, what was our carbonyl group, and so then we're going to make the full-blown acetal. So two equivalents will produce the acetal. Now, we talked about equilibrium in the last lecture in terms of hydrates and acetals and ketals. It turns out that for normal run-of-the-mill aldehydes and alcohols, the equilibrium lies towards the reactants. So we really don't form much product, much hemiacetal or much acetal, although those cases, there are some cases where we do form it. But for the most part, the equilibrium lies to the left. Now, one of the ways that we can make the equilibrium go to the right is by forming a cyclic acetal or forming a cyclic ketal. What would that involve? Well, here's a typical case. Let's take our just normal aldehyde, and now let's react it with a dialcohol. And I'll put in the CH2 groups for the moment. This is called ethylene glycol. Ethylene glycol, there's a couple of uses for it. It's used in this organic synthesis. It's also a component of antifreeze, so most likely if you put antifreeze in your car, it's going to be ethylene glycol. There is another more environmentally friendly, which is called propylene glycol. And organic chemistry is one of those things where a carbon makes a huge difference. A huge difference. Give you a couple of examples. Methanol would, if you drank that, blindness or death. Take your choice. ethanol in moderation, okay, in excess, you can fill in the blanks. But methanol is a poison. Ethanol in high concentrations is a poison, but you do not drink methanol. So 1 carbon makes a huge difference there. Ethylene glycol is a poison. One of the things, if you're changing or adding antifreeze in your driveway, if you spill some, it would be best if you didn't if you spill it, immediately sort of collect it up. Animals find it to be very sweet, and so they kind of will come and they will lap it up, and they will either get sick or die. So this is the non-environmentally friendly antifreeze. However, there is an environmentally friendly propylene glycol with an extra carbon in it, and that is actually much less toxic. So 1 carbon makes a difference. We're not going to use propylene glycol, although we could. We're going to use ethylene glycol to do this reaction. So we're going to react the ethylene glycol molecule with an aldehyde in the presence of acid. What we're going to get is, if you think about this side of the alcohol and then this side of the alcohol being alcohol molecule number 2, what we will get is the first side, and we'll go through the entire mechanism here in a moment. We'll get the first side of the alcohol adding to the carbon to form the, in this case again, this is the Hemiacetal. And then continuing on, and we should have equilibrium arrows here. Continuing on, this side of the molecule will now react so that in the end, what I'm going to do is I'm going to actually add both sides of the molecule to make then a cyclic acetal in this case. So this side of the molecule will then wrap around. I'll show you, and then we'll do the mechanism in a moment, to then form the acetal with both of the alcohols. It's just that both the alcohols in this case are attached to the same set of carbons. In this case, because we're forming a cyclic acetal, or if we formed a cyclic ketal, the equilibrium in this case lies towards the products. So when you make a cyclic acetal, you actually form it in a very high yield, and you push the equilibrium to the right. Okay. So all I'm doing is reacting the aldehyde with 2 alcohols again, but I'm connecting them so that I form a cyclic ketal and a cyclic acetal. So what does the mechanism of this look like? Well, I need a blank slide, which I should have put in. Blank slide, come on. Whether we'll get to all these today or not, we'll see. Blank slide. So let's write the mechanism for that reaction. Instead of using an R group, let's go ahead and use a CH3, CH2. Let's use an aldehyde. So now let's react that with our ethylene glycol molecule and our H+ acid catalyst. So if you wanted to, if you were an overly ambitious go-getter student, you could stop the video right now and you could do the first couple of steps of this mechanism. What would those be? Take the carbonyl group and protonate it. Right, we protonate the oxygen, and then 1/2 of the ethylene glycol molecule, one of those OH groups is going to come in and add to that carbon, and in this resonance structure we would give that pair of electrons to the oxygen. And you're going to be surprised how much this mechanism is exactly like the other, because it's the same mechanism. Okay. So we add one of the OHs to the carbonyl, and we make our Hemiacetal. Now, we're going to lose our H plus here from, again, we add the entire alcohol molecule, so we're going to lose that. And I'm going to write it over here to make it easier to write. Okay, so we're then going to form that hemiacetal. It was a protonated hemiacetal before. Right, so now we're going to react the OH group with the H plus that just came off. To form the oxonium ion. Next step, say it with me, lose the water to form the carbocation. Should probably put in my lone pairs over here. And so what happened before was a second equivalent of alcohol would come in and react with this carbocation. But now what I'm going to do is I'm going to take the other OH group and I'm just going to wrap it around and add it to the oxygen. Now, there's a couple ways to draw this. We can draw it like I had shown before. So in other words, let's take the carbon and let's put the hydrogen there so that we have our O with our CH2, CH2, now with our other oxygen, with our H as our oxonium ion. So we're basically forming, let me move these out of the way. We form that oxonium ion by adding the entire alcohol. And then, of course, we're going to lose our proton in the final step, because remember, acid is, this acid up here is the catalyst. And so we're going to end up forming a 5-membered ring. So in this case, we're forming our cyclic acetal. And it's an acetal because it comes from an aldehyde. So the equilibrium would lie then towards the formation of this cyclic acetal. Okay. And usually with an aldehyde or a ketone, we do use ethylene glycol as our dialcohol, as the dialcohol to form the cyclic acetal. So this mechanism is going to be the same whether it's a ketone or an aldehyde, but typically what we do is we use the ethylene glycol because it's easy to get on and it's easy to get off and it's relatively inexpensive. Okay, so I can make the cyclic acetal. Now let me also kind of introduce the idea of, is that the only kind of cyclic acetal or cyclic ketal that we can make? Are these the most important? They are in synthesis, and I'll show you why in a few minutes. But you've encountered molecules that look like this. in your biology classes if you've taken them. And I'm just going to write some generic structure here. And what kind of molecule is that? It's a sugar or a carbohydrate. Is this the normal way that you see a sugar or a carbohydrate in your biology class, and the way you will write them certainly in biochemistry in the future? No. So what happens with these compounds? What happens with these is that usually one of the alcohols down here will react with the carbonyl to form a cyclic, in this case, a cyclic hemiacetal. So in terms of writing the structure for that, let me give you a couple of tricks here. Number one, always number your carbons so that you don't get lost. So if the oxygen reacts with this carbon, that carbon is going to have an H attached to it. It's going to have the OH group that the carbonyl oxygen becomes, and then it's going to have another oxygen attached to it from this OH group. What size ring am I making? Well, I've got 1, 2, 3, 4, 5, and then oxygen is atom number 6 of that ring. So what I'm going to end up forming is I'm going to end up forming a 6-membered ring with the oxygen as number 6. So let's go 6, 5, 4, 3, 2, 1. Carbon 1 then has the OH and the H. So carbon 1 was the aldehyde. It is now a hemiacetal. Again, it's an acetal because it started out as an aldehyde. What's attached to carbons 2, 3, and 4? Just simply OHs. I'm not going to put in the stereochemistry here. I'll show you that in a moment. And then what's attached to carbon 5? A CH2OH. So this is the cyclic form of a sugar or of a carbohydrate. And it is a cyclic hemiacetal form. Okay. So you've seen these kinds of molecules before. You just haven't necessarily talked about them in the context of them being cyclic hemiacetals. So let's go back in my notes here and let's take a look at exactly what I'm talking about. So, in terms of sugars and carbohydrates, these are all either called aldoses, or in some cases, they're different aldoses if they come from an aldehyde. So, for instance, you can have one carbon, you could have a 3-carbon aldehyde, and then you can have a 4-carbon aldehyde and a 5-carbon. So these, in biochemistry terms, and it's been like 30 years since I've taught this, is an aldotriose, an aldotetraose, pentose, and an aldohexose. The aldohexose is the one we mostly deal with, but you've seen these names before: erythrose, xylose, glucose, galactose. Those are all of our sugars that we think about in biochemistry or in biology. So all of these, well, not all of them, but the ones that are large enough at least to form 5- and 6-membered rings can certainly do so. So here's an example of glucose, and it's what it's called as linear form. Well, as I said before, the OH can come in and react with that carbonyl group, and we'll end up with then the cyclic form of that hemiacetal, which would be called a glucopyranose. The D's, I'll come back to the D in a moment. The idea here is alpha So alpha means that the OH is in the down or axial form, and then the H would be equatorial. Remember, these sort of Hallworth projections you see in biology, but we learned that the Hallworth projections really should be some type of cyclohexane ring. You can have ketoses. If you have fructose, for instance, if you take fructose and it is a ketone, it has a ketone at carbon 2. So if the OH comes in and forms the cyclic ketal, or cyclic hemiketal, what you end up with is you end up with a fructose furanose. And and I'll show you in a moment, if you combine the glucose and the fructose, you end up with our common table sugar, which is sucrose. So you can end up with both ketoses and aldoses as molecules with these cyclic hemiacetals, or in this case a cyclic hemiketal. The equilibrium for these is that when you put glucose in water, only less than 1% of it is in the open chain, and the rest of it is either in the alpha form where the OH is here, or in the beta form where the OH is there. And you can actually see the beta form is favored over the alpha form. In your book, that's called the anomeric effect. I'm not going to really get into that. You can get into that in biochemistry. This is a huge difference, though. Having it beta versus having it alpha can mean complete reactivity or not reactivity with a sugar, or in this case a hexoaldose, or an aldohexose, I guess. You can link these rings together to form cellulose. Remember, all cellulose is linked glucose molecules. And I guess that's it. So when you see sugars in the future, you can think of them as hemiacetals. In this case, because I'm forming a linkage, and there's still hemiacetals or hemiketals. Okay. So that's sort of where all of these hemiacetals and hemiketals come into play in biochemistry, in molecular biology and genetics and biology. So let's talk a little bit more about using cyclic acetals and ketals, and let's talk about protection. Now, protection is going to sound an awful lot maybe like blocking. It's slightly different, but it's going to be a similar idea. Although, wait, we talked about protecting groups. We need some review. Here's our review. And should I make... No, I won't make this part of the online quiz that you have to go back and look in your notes. I should, but I won't. So let's say we talked in the past about protecting this OH so it would not undergo any kind of reaction. What we could do is react it with our trimethyl silyl chloride. I believe that was exam 1, so that we could protect the alcohol so that it would not react in whatever I wanted to do with the carboxylic acid here. Then when I want to take the trimethyl silyl group off, remember this was called a silyl ether. When I wanted to remove the silyl ether, I just used fluoride in water, and that would strip off the silyl group and return the alcohol. So we ended up with the fluorine attached to silicon. And the driving force for that is this formation of a very strong silicon-fluorine bond. So we've done protection before. This molecule would basically be a protected alcohol. So one of the things we can think about is using cyclic acetals and ketals as protecting groups. There's a couple different ways we could do that. So let me just think if I can make up a molecule here where, let's say I've got a ketone and over here I've got a bromine. This is my standard example. Now, if I had this molecule and I wanted to form this molecule, in other words, I want to replace the bromine with a carboxylic acid, how would we do that? Again, I should make this a quiz question, but what we would do is we would react the bromine with magnesium and then CO2. And that would add the carboxylic acid group to the end of the molecule. Well, there's a problem in this case. And here's the problem. The problem is that when you form that Grignard, right? The magnesium would react with the bromine to form this Grignard. We normally just, because we're writing one molecule on paper, we don't think about the bazillion molecules that are in solution when we're actually doing this reaction. So when we make this Grignard, the problem is that this carbonyl group is exactly what Grignards react with. So you could have a situation where maybe this C- will wrap around and attack that carbonyl to form a ring. In this case, it would form a 1, 2, 3, 4-membered ring. Probably not possible, but the other thing that would happen is there's certainly another carbonyl molecule in there. And so once I form that Grignard, that C- could come down and attack the carbonyl of another molecule, and it would go ahead and make that alcohol. The whole thing is whether it forms a cyclic compound by this would be the intramolecular reaction, and this would be the intermolecular reaction. Either way, that's not what I wanted. I wanted to make the Grignard and then react it with CO2. So if I just do this reaction as it stands, I will not get that product. Okay? So this is where protection comes into place. What if I could protect the carbonyl group, the ketone, from reacting with the Grignard, react my CO2, and then come back and take my protecting group off? So how would I do that? I'm going to need another blank slide. And when you see these slides online in the folder, I'm going to have them rearranged for you. All right. So how would I do a protection here? Before I make the Grignard, what I'm going to do is I'm going to react that ketone with ethylene glycol and acid. And what's going to happen? I'm going to form the cyclic ketal in this case. That's a cyclic ketal. That means the equilibrium is pushed to the right. The question is, okay, so how stable is this cyclic ketal? It's very stable. It will be stable to every reagent. So it's going to be stable to every reagent. And here's the big exception. except H plus and H2O. And what happens when H plus and H2O are added? The equilibrium reverses and it goes back to the ketone. Okay. So I want to turn this alkyl halide into a Grignard. Am I using H plus and H2O? Not yet. So I'm going to make this Grignard. That Grignard is essentially a basic reagent, not acidic. Water can't be present at all. So that protected ketone will not react with the Grignard. So now I've made my molecule. Now I say, you know what? I'm going to react this with CO2. I'm going to write out the structure of the CO2. The C minus is going to come in, attack the carbonyl, or one of the carbonyl groups. Well, it's going to react with CO2, and I'm going to end up then adding forming this molecule with the minus charge. If you're concerned about the counterion for that, is going to be magnesium bromine plus. Okay. So I just added my CO2 group. There was no danger of it reacting with the cyclic ketal, because cyclic ketal only reacts with H plus H2O. So now what I want to do, I want to add acid and water to protonate the carbonyl group, or to protonate the carboxylic acid or the carboxylate group. I also want to deprotect my ketone and reform it. Beautiful. I can do that in one step. Add H plus H2O to that. And what happens? What happens is the cyclic ketal, or cyclic ketal in this case, goes back to forming a ketone. And I protonate my my carboxylic acid to make the product that I wanted. So this is another example of protection and then deprotection. Okay. So this is a very useful reaction with the with aldehydes and ketones to protect them as cyclic acetals and cyclic ketals. And then you can do reactions, and then you end up stripping them off at the end. I'm going to show you a version of this that is kind of related to the sugars. So if I draw out sort of a Hallworth projection, which is the flat cyclohexane ring projection of some sort of sugar molecule. It might have a CH2OH down here. I'm going to have an OH here, and then I'm going to strategically put an OH there. In sugar chemistry, the goal is to basically one by one replace each one of these OH groups, not replace it, but add something to it. For instance, a lot of drug molecules need to get into cells. And there's a problem. Cell wall doesn't necessarily like the drug and won't let it pass. So a lot of times what people will do is take these sugar molecules and they will attach off the oxygen. They'll attach some sort of drug molecule. So when the cell wall is like, oh, sugar, come on in, and then it drags the drug molecule in it, and it either does something healthy or not healthy to the cell. If it's a cancer cell, we want to take a drug in and kill it. So in sugar synthesis, you have to sequentially replace these or add groups to these OH, but the problem is they're all OHs, so how do you differentiate between one or another? And that's where there's different protections strategies that are used, and I'm not going to get into all of them, but I'm sure there's many online. I'm just going to show you one that's actually pretty easy to understand, and that is, if I erase my lines here, I could think of these two OH groups, they're cis, whereas this OH over here and this OH over there are trans, and this OH and that OH are trans as well. What's my point? My point is that I could take a molecule like acetone, right? Dirt cheap, low boiling point. Let's say I reacted this sugar molecule with acetone and H+. Now we just looked at protection as protecting the ethylene glycol, using it to protect the ketone. I'm going to get the same reaction here. My only requirement is that those alcohols need to be cis, because otherwise I can't form a 5-membered ring, because 5-membered rings cannot be formed underneath and on top of the ring. They've got to be on the same side. So what I'm going to do is I'm essentially going to use the acetone molecule to protect those two OH groups. So if I rewrite my structure here with my OH here, my OH here, what I'm going to end up doing now is I'm going to end up now forming that cyclic acetal. So in essence, you could think, well, the sugar's protecting the ketone, and actually the acetone is protecting the sugar. But the restriction is those two OH groups have to be cis. Why would I do that? Well, because now what happens is those two OHs are no longer able to be reacted. So maybe I choose this OH or this OH, and I could go ahead and add something to each of those, and then when I'm done, strip off the basically strip off the protecting group, and I've got those other two OHs free to react in another way. So if you're doing sugar synthesis, or any kind of synthesis that involves these kinds of sugar molecules, you spend an incredible amount of time protecting and deprotecting. You spend almost as much time, or sometimes more, protecting the groups than you do actually adding something to the other OH groups. And so that's doing sugar chemistry or doing sugar synthesis is its own area, simply because you have to somehow make those OH groups different. So that's another example of a way to protect, but in this case I'm protecting the dialcohol instead of protecting the ketone. Okay. So the idea here of protecting, the idea of doing this protection is important. Okay. So let's talk about another synthesis that's actually in the Top Hat book, and that is to use thioacetals and ketals to prepare ketones and aldehydes. Now, a thioacetal, the one that's commonly used, is this. Thio means sulfur. So let's say I take this dithiol and I react it with a carbonyl. And typically the carbonyl that we would start with is something like formaldehyde. So if I do this reaction, and you don't actually even need acid for this, what will happen is that we'll form, the sulfur will then react, the two sulfurs will react with the carbon, and because we have an extra carbon in here, instead of forming a 5-membered ring, we're going to form a 6-membered ring. And so we make this molecule. Now, what I can do with this molecule is I can treat this molecule with something like, well, treat it with a strong base. The strong base that's typically used is this molecule called butyl lithium. Basically, it's a C-, it's a Grignard. So what it will do is come in and pull that hydrogen off. And so what I end up doing is I end up forming a C-. I deprotonate this hydrogen and I make a C-. Now that C- is a nice, strong nucleophile. And what can I do with it? What can't I do with it? I could take that molecule and I could react it with, how about I react it with an aldehyde? This C- is like a Grignard. It'll come in, attack the carbonyl. I will end up with the O- here. And then my carbon will have those 2 sulfurs attached to it. But basically this large group is nothing more than the R- of a Grignard. And then I could say, okay, when I'm done with that, let's go ahead and react that with H+ and H2O. This thiolate, or this thioacetal in this case, this is a thioacetal. It's an acetal with sulfur. Same thing is true. It is stable. It's stable in everything but acid and water. So when I add acid and water, I'm going to remove the thioacetal and convert it back to the ketone. I'm going to end up with an OH here, an H there, and then down here I will have added my aldehyde. So I started with formaldehyde, and what did I just do? I just added that entire group. Okay. Now that's not what the slide says. The slide says, well, how do you prepare ketones and aldehydes? Well, that's actually in the book, and they showed that as a separate reaction. So if I go back to my C- molecule, I want to prepare an aldehyde. All right, how about I react this with ethyl bromide? Now with these molecules, the C-, I know Grignards didn't do this, but these molecules do. It would do an SN2 and come in and react with, and this has to be a primary halide. So what I would end up doing is I would end up adding a CH2CH3 group to this. Again, my 6-membered sulfur rings would be there. And if I want to stop, I'd say, okay, let's add H+ H2O to this. And now what have I done? I've now basically added the ethyl group to the aldehyde, starting up here with formaldehyde. So I replaced one of the hydrogens in formaldehyde with an ethyl group. But think about that. I mean, any primary halide, I can add any group over here as long as it's primary. I can add any group I want over here, so I can custom synthesize any aldehyde I want. Okay. Well, what about, it says prepare ketones and aldehydes. So preparing ketones and aldehydes, what would I do there? Again, I have my C- along with my sulfur. So I could say, well, actually, let me just, okay, I did that reaction and I added my ethyl group. So I want to make a ketone. How about another equivalent of butyllithium? Butyllithium, that's the C minus, not an O minus. The butyllithium comes in, deprotonates. I now have my strong nucleophile. What do I want to put on the other side? Now let's put a propyl group. That's now going to come in, do an SN2 reaction. So that now there's an ethyl group on one side, now there's a propyl group on the other side. I add H plus H2O to this, and what happens? I now have synthesized a ketone where I chose the group to the right of the carbonyl and I chose the group to the left of the carbonyl. So it's a really good method using these thioacetals and ketals. It's a really good method to make ketones and customize the groups that I want on either side. Now, I will say one thing that you'll probably see in the book here. In the book, they probably add mercury 2 plus to this hydrolysis to react with the thioester with H plus H2O. The reason that the mercury is there is to help yank the sulfurs off. The mercury-sulfur bond is incredibly strong. And so if you have a hard time breaking a carbon-sulfur bond, sometimes what you need to do is you need to throw in some mercury because that'll help remove the sulfur and break the carbon-sulfur bond. Okay. So the theme for today has been making cyclic ketals and acetals, and then also then using a sulfur molecule to make this. The other thing I'll add in the book is that this, I don't know why they introduced this term. This takes me back to graduate school. The book talks about umpulong, that this is an example of umpulong. What is umpulong? Umpulong is basically opposite of what you would think. If I had a carbon attached to a sulfur bond, if I had a C-S bond, I would normally think the sulfur's negative and the carbon's delta positive. So by using this methodology, what I did was I reversed it. So now the carbon is negative and the sulfur isn't. So that's an example of umpulong. So what I can do is I can basically use the sulfurs to make a C minus. Normally the sulfur would be minus. Okay. Okay, so my time is up according to my timer. And so what we will do next time is we will pick it up and talk about the remainder of chapter 23 and move into the end of chapter 22. We'll move into chapter 23. And we'll start by talking about reactions, oxidation reactions of aldehydes and other reactions of aldehydes and ketones. Okay, so there will be an online quiz for you to do for this, and also read the appropriate sections of Top Hat and do those problems that are within those sections.